Yeah, it's 10, I think. So, should we start or?
Yeah, we better start, yes.
Good morning. I, Angana, on behalf of the Department of Physics, IIT Guwahati, extend a warm welcome to you all for the celebration of National Science Day 2021. The department has been celebrating this day for the last few years, and this year the celebration is focused on the topic Future of Science, Technology, and Innovation Impacts on Education, Skills, and Work. Without any further ado, I request Professor P. Paulus to take over as the chair of the first session. Sir.
Thank you, Ankana. So, good morning to everybody and warm welcome to all of you. So, I'm really happy to be part of this and then see that the department is consistently for the past few years organizing this, and very happy to have our guest, Professor Shobhana, here. So, we have some wonderful talks which have lined up. Before that, we invite our head of the department, Professor Supradeep Ghosh, to inaugurate the program and address the meeting. Supradeep.
Thank you, Paulos. Very warm welcome to you all for this edition of the National Science Day. I feel a little awkward in the sense that, till last year, we used to have it completely offline. So it was kind of a little bit, I would say, a pompous affair. People used to gather together. We had guests and people from other departments also used to join sometimes, and it was a day-long affair. It used to be a day-long affair, but because of this COVID crisis, we had to curtail down a lot, and we thought that this year there's no point, having a day-long meeting because people are already tired of several online meetings and everything. So let's keep it kind of short, but let's keep the tradition going. And in fact, I would like to give the credit to Paulos, who was HOD before me. He had started it all, and we are only carrying that forward. So, as Paulos had already said, that we have a number of interesting talks still, starting with Professor Narsiman. The theme this year is has a very wide scope and also somewhat difficult, I would say. So, from the department's point of view, seeing the future is very difficult, but what we are doing is we keep on going and try to train as many as human resources as possible by pulling our weight behind. In fact, even in this period of COVID crisis, we haven't really stopped that, tried to reach out to the sections of the society where there are little resources. We have a very strong sort of outreach team when it was possible to do offline. They were doing exemplary work that included our staffs and students and some faculties also. So even during this COVID period, we have tried to do that because we believe sincerely that the future of science, innovation, everything lies in them. So from our point of view, we try to bring them or sort of create scope for them so that we get a sort of dreamy future and so on. So with this, I would once again like to welcome you all, and I hope that with this limited arrangement, still it would be a resounding success. Thank you.
Yeah, thank you, Supradeep. So, we should start with the keynote address, and we are very happy to have Professor Shobhana Narasimhan with us as the keynote speaker. So, although we all know her very well, she is very well known in the physics circles, not only in India but abroad as well, globally. But just for the younger audience, maybe I will give a brief introduction about her academic program and other these things. So She completed her master's from IIT Bombay and then moved on to Harvard University for her PhD program, working with the theoretical condensed matter physics group there. And after her PhD, she moved on to Brookhaven National Laboratory for a brief time, and then to the as a Max Planck Fellow to Fritz Haber Institute of Max Planck Society. And then she joined Jawaharlal Nehru Center for Advanced Science Research in Bangalore in the institute's young age itself, and as a faculty member there. And she has been there since then, and she is a professor now there in the theoretical sciences unit there. And she has been doing wonderful research activities and then various other academic activities in the nation and globally, and keeping in touch with many of the European as well as other global institutions, including the Max Planck Institute, ICTP, etc. Professor Shobhana's research interests span many aspects of content matter system, including the bulk properties of the metals, studies on alloys, carbon-based and other, and then nanomaterials. So she has more than 80 research publications in this short period. And presently, she is leading the research group working in computational nanoscience at JNCSR. And along with these wonderful research activities, she has been mentoring young researchers, many of them. And she takes also keen interest in pedagogy development and developing innovative teaching methodologies, tools, some of which have found its way to various renowned teachers in, for example, University of California, Santa Barbara, MIT, etc. They are using her kind of the tools that she has developed. And she has, as I said, she has many PhD students mentored, postdoctoral fellows and master students, and then she has been really training also the younger undergraduate students as well in Bangalore. And she especially has been involved in helping women in science in India and abroad, in fact. So she has been the standing committee, member of the standing committee for promoting women in science. This was constituted by the DSTA of Government of India, I think about maybe 10 years or ago, or slightly less than 10 years ago. And she has been instrumental in organizing many career development programs for women, not only nationally, but also along with ICTP and also with other institutions like East African Institute, etc. Her contributions have been recognized by the community in various ways, with honors and awards conferred on her. Some of them include the International Union of Material Research Scientists Young Research Award, which she received almost immediately after her PhD in '98. Material Research Society of India Medal in 2001. Kalpana Chawla Women Scientist Award of Government of Karnataka in 2010, Sri Shakti Saman Science Award in 2010, and we should not forget that as a student also, she has been wonderful. She has been the topper in all her undergraduate classes and master's class in IIT Bombay. She received the silver medal from IIT Bombay, and she is a fellow of National Academy of Sciences of India since 2011. So we are very happy to have her here today. And thank you, ma'am, for joining us, taking your time out to talk to us on a wonderful topic. Basically, this is in line with the theme of this year's National Science Day, which is Future of Science and Technology in India, Impact of Education, Skills and Works. So her talk is titled The Role of Science and Scientists in Shaping India's Future. So on behalf of all of you, let me welcome Professor Shobhana Narasimhan once again. Ma'am, please.
Thank you, Professor Paulos, for that very extended introduction and very kind introduction. And thank you, Professor Ghosh, for inviting me to give this talk. Y'all can see my screen and hear me? Hello?
Yes.
Yes,
Okay.
yes.
Okay.
Yes.
So I've titled my talk, The Role of Science and Scientists in Shaping India's Future. This is the cover of a comic book that was recently brought out, which shows this superhero called Nagraj fighting the coronavirus. So I thought it was apt for these times. I'm not used to giving talks on a topic like this. In fact, when I was preparing the talk yesterday, I began to be a little annoyed with myself, and I thought I should have just given a straight scientific talk on, something like how nanoscience or quantum technologies will help India's future or something like that. So this is a little bit outside my comfort zone. And long ago, my mother gave me this book of cartoons by R.K. Lakshman. I suppose at least the older people here will have remembered him. He was a famous cartoonist. And this is a book of his science cartoons. And I remember this cartoon from his book. And it says, now the professor will give a short talk on the scientific temper in the context of cooperative movements in developing countries in relation to international implications and technology of coordination. And I felt I had sort of let myself in for some talk like that. And since some of these topics are a little bit controversial, though I'm trying to avoid controversy, I think I should make it clear right at the start that what I'm saying are my personal opinions. They're not the opinions of JNC where I work or IIT Guwahati. And I really do not intend to comment on politics or religion. So let me start with a little bit of history. So as most of you know, debates about the role of science in shaping India's future are as old as modern India. And at least the usual view is that the original debate, you can sort of see it as the two sides were the Gandhian view and the Nehruvian view of how India's future should progress, what kinds of technologies it should adopt. And people often say that Gandhi was anti-science. So I was reading some of his statements on science. It's a little hard to parse what he actually meant. For example, there's this quotation, "The boast about the wonderful discoveries and the marvelous inventions of science, good as they undoubtedly are in themselves, is after all an empty boast." So I'm not quite sure what to make of that statement. Certainly, he opposed vivisection, which is the practice of performing scientific experiments on live animals. Incidentally, this picture of Gandhi looking through a microscope is something I like very much. And about vivisection, he said, "I abhor vivisection with my whole soul. I detest the unpardonable slaughter of innocent life in the name of science and humanity so-called, and all the scientific discoveries stained with innocent blood I could count as of no consequence. If the circulation of blood theory could not have been discovered without vivisection, the humankind could well have done without it." Now, of course, as scientists, we usually think of Harvey's discovery of the circulation of blood as one of the big scientific discoveries that have been made in biology. So we may not agree with him. But of course, this debate about experimentation being done on medical experiments being done on animals is an ongoing one. And there are a lot of animal rights activists even today who oppose this. So It isn't totally a marginal view. One of the most controversial statements he made was in 1934, as many of you may know, when there was a big earthquake that devastated parts of Bihar and Nepal, and lots of people died. And he said, "You may call me superstitious if you like." I highlighted that to say, he was well aware of what he was saying. I think it was a very deliberately made statement. He wasn't unaware of, I think it was a deliberately provocative statement. He said, "But a man like me cannot but believe that this earthquake is a divine chastisement for the great sin we have committed and are still committing against those whom we describe as untouchables." And famously, Tagore was very upset by this statement and wrote to Gandhi, and this is an excerpt from his letter. He said, "It is all the more unfortunate because this kind of unscientific view is readily accepted by large sections of our countrymen. I keenly feel the inequity of it when I'm compelled to utter truism in asserting that physical catastrophes have their inevitable and exclusive origin in certain combinations of physical facts." Now, Nehru, on the other hand, this is, I think, a very nice picture of Nehru with Einstein. And he had studied chemistry himself at Cambridge. And he said, "I too have worshipped at the shrine of science and consider myself one of its votaries." A votary is somebody who worships. It is a nice quotation, though it sort of disturbs me because I feel science should not be seen as a shrine and it should not be worshipped. But he certainly was very aware of science. And this quotation I like much more. This is a picture of him with C.V. Raman, whose discovery we are celebrating as National Science Day. He said, "What is needed for India is the scientific approach, the adventurous and yet critical temper of science, the search for truth and new knowledge, the refusal to accept anything without testing and trial, the capacity to change previous conclusions in the face of new evidence, the reliance on observed fact and not on preconceived theory, the hard discipline of the mind." I think these are all beautifully crafted phrases, and they completely show that he was well aware of what we see as the strengths of science and the scientific method. And he says all this is necessary not merely for the application of science, but for life itself and the solution of its many problems. What did the scientists say to this debate? So Saha, for example, he said, "One comes across overdrawn pictures of the imaginary good old days when nobody was supposed to have anything to complain of and a tendency to attribute all the troubles of the world to the evils of science." And I think this was pretty much a direct attack on Gandhi, this statement. He says, "We do not for a moment believe that better and happier conditions could be created by discarding modern scientific technique and reverting back to the spinning wheel, the loincloth, and the bullock cart." So I tried to think about what I felt I wanted to say about the role of scientists in shaping India's future. And I thought what we really need to do is, obviously, we should contribute to the advancement of general scientific knowledge. And then apart from that, maybe we should focus on certain things. So we should work on important problems that meet societal needs, like combating disease, meeting energy needs, reversing climate change. Then we should educate future generations, which clearly everybody at IIT is doing. And then these are all the standard things, but then I thought it's rather important that we should focus on something that we don't spend enough time thinking about, which is foster rationalism and scientific temper, fight superstition, especially if it is harmful, and contribute to discussions about equity. And as I go from the top to the bottom of this list, I feel we are moving more and more of our comfort zone as practicing scientists, but it is rather important that we move out of this comfort zone. So let me talk about each of these points a little bit. So contribute to the advancement of general scientific knowledge. So there's been a lot of debate over the last couple of decades where people say that Indian science has failed. Indian post-independence science has failed. Now, how do people judge this? They say that, oh, we haven't won the Nobel Prize. That's the standard thing, okay? Even our political leaders sometimes say, oh, we've funded Indian science for 50 years, we've put so much money into it, but not one Nobel Prize has come out. So why should we continue to fund science? Okay, then people say, okay, why don't we get Fields medals? And then, Narayan Murthy, industry leader, he says no invention, earth-shaking ideas come from India in 60 years. So of course, I'm sure you will agree with me that one should not measure the success or failure of Indian science by whether we won a Nobel Prize or not. And we may not have won a Nobel Prize, but certainly scientists working in India have won many of the other major scientific prizes. And there have been several successes of Indian science. One big success is, of course, the Green Revolution. Then there are smaller scale successes like the development of the Jaipur foot, which is a prosthetic foot, which has helped many, many people, and people from all over the world have been coming to Jaipur to get fitted with this. And we should ask ourselves, when they say we funded you and you are not producing Nobel Prizes, is it indeed that well supported? So this graph shows the percentage of the GDP PPP. PPP means adjusted for per capita purchasing parity and purchasing power. And you see this graph shows how much of their GDP, what percentage of their GDP various countries which have strong scientific programs support, spend on research and development, spend in supporting science. And you see that we are spending a much, much smaller percentage of our GDP than, certainly than Israel or South Korea, but even than, USA or France or Germany. Significantly smaller than China, which is something that which is a country we keep comparing ourselves to. And so, if they use this, and now, I mean, people keep saying we're supporting too much, we're spending too much money on science, people keep threatening to cut our budgets. And if they cut our budgets even further, we're going to produce even less, I believe. Okay, but then of course, we are not a rich country. We are not a wealthy, developed country. So we have to ask ourselves, why should a country support scientific research? And is supporting scientific research a luxury for a developing country? And also, if you're going to support science, you should ask yourself, should we be supporting basic science at all, or should we only be supporting applied research? And increasingly, there is a tendency in our funding agencies to say, what are you doing? Why are you doing it? What's going to come out of it? What product is going to come out of it? How is it going to benefit our country in the near future? So why should a developing country support basic research? This is again a cartoon from Lakshman's book. And it's sort of imagining prehistoric times where some guy is sitting and trying to develop the wheel, and people are unappreciative and saying he won't go far doing that. He calls them wheels. So obviously in science, you don't know it's hard to predict really what is basic and what is applied. So yesterday I was having a WhatsApp chat with one of my friends, Nicola Marzari, who's a professor of physics at the EPFL in Lausanne in Switzerland. And I was saying, I'm trying to think about why we should support research and why we should support basic research. And what he typed to me is, he said, knowledge is empowering and knowledgeable societies are more resilient. And I thought that was certainly a very interesting statement. And so I texted him back and said, thanks, I'll use that. So I have done that. I have just shown you his text. But so UNESCO brought out this book, which says, it's quite a long time ago, actually. It says, no culture, no civilization which neglects this aspect of scientific and technological endeavor can be counted whole or complete. Now, that may seem a bit pompous, but I think there's some truth in it. And then paradigm shifting ideas often come from basic research, okay? So, I mean, there are very famous examples that I'm sure you're all well aware of. For example, X-rays revolutionized medicine, but when Röntgen was working on X-rays, he certainly wasn't looking for a medical imaging technique. He was just investigating, the properties of some radiation that he was finding in these materials. There's a risk of falling behind, having to depend on developing countries for ideas and expertise. I think this is something we're really seeing right now in coronavirus times with vaccines. Only a few countries have the skills to develop the vaccines. And those countries that don't have those skills are completely dependent on these other countries to do the testing, to give them the advice, to give them the vaccines. I think GM crops is another area where you see that certain countries are trying to dictate to others what policies they should follow. And a scientific workforce trained in basic science can be flexible and adapt easily to tackle complex scientific problems that may arise and impact society. Again, I think coronavirus is a perfect example of this. We've seen that to tackle coronavirus, you need people who are trained in statistics, people who are trained in biology, people who are trained in mathematical modeling, people who are trained in electrostatics to look at how to make masks more effective. And if they didn't have all this expertise, which they have mostly
I think you muted yourself.
Yeah, Shobna, I think you muted yourself.
Yeah, please unmute. Or maybe we can unmute her from here.
Yeah.
Try that. Subradeep, I think you can do that.
Yes, I'm trying that. Uh-oh.
Okay, is it now? Can you hear me?
Yeah, now we can hear.
Okay,
Yes.
it's very strange because I didn't touch the screen. Okay, I apologize for that.
No problem. We just lost you for half a minute or so.
Okay, anyway, I'll just go ahead.
Yeah.
Okay. So I think another reason why we should support basic research is, I think, the feel-good factor, national pride. I think that's quite important actually in capacity building for the future. Like when, the Chandrayaan-1 mission was successful and we found water on the moon, I think we felt great pride. I mean, it's the kind of pride we feel when our cricket team beats the English team within 2 days. It really, it's something unquantifiable, but I think it's quite important. We should educate future generations. I didn't want to say too much about it because this is something that you all know much better than me, and who am I to talk to you about it? But I thought since we're celebrating Raman's discovery, I should say a little bit about him. So I thought I'd quote this saying from him. He says, it's generally believed that it is the students who derive benefit from working under the guidance of a professor. In reality, the professor benefits equally from gifted students working under him. And certainly a success a great success in Indian education has been the IITs, and this is a quote from Vinod Khosla, who was educated at IIT and went on to found Sun Microsystems and is a billionaire. And this is when 60 Minutes program in the US did a episode on the IITs. He said, when I finished IIT Delhi and went to Carnegie Mellon for my master's, I thought I was cruising all the way through Carnegie Mellon because it was so easy relative to the education I'd gotten at IIT Delhi. So I thought I should show my group, my students, my postdocs. The picture on the left is all of us. The picture on the right is me with some of my female students when we were in Paris at the Eiffel Tower. And I know we're doing some weird actions there. That's because we used to joke always that I was like the mother bird and they were the baby birds with their mouths open waiting to be fed. And so we're all sort of pretending that we're birds in that picture. And we do continue to keep in touch even after they have left the group. So for example, this is a recent picture where this was a Zoom meeting of just many of the women who have been in the group over the years. Some of them have faculty positions now. Some of them are postdocs. 2 of them were on maternity leave at the time this Zoom session happened. 1 of them actually even had to drop out because of family constraints. But we get together and we discuss our work, our problems, our life situations, and I think I get as much from them as they get from me. I used to worry a lot about the fact that by devoting myself only to my research, I wasn't contributing enough to society. And so I started various activities a few years ago, and one of them was teaching physics in other developing countries besides India. So I have been going regularly to Africa and have been teaching. The picture on the left, so that's me in the red sweater at a workshop in South Africa. The picture on the right is me with 2 of the women, one from Cameroon and one from Kenya, whom I have mentored. We may think that we're a developing country in India, but our scientific institutions and our scientific education is so advanced compared to what exists in several other parts of the world. And we can contribute a lot by sharing our expertise with people in some of these countries. And I would really urge all of you to think about it. For example, something we could all do is mentor students in other countries who are desperate for people who just want, they want a little bit of advice. Sometimes it's just, 2 or 3 sentences I've said to some of these students, which they say change their whole career or change the course of their PhD thesis. So part of this thing about contributing to society is to work on important problems that meet societal needs, like combating disease, meeting energy needs, reversing climate change. Now, those of you who are faculty, I'm sure you would have applied for grant proposals recently. And then they always ask us, show how your proposal is aligned with national priorities. And you have to take, Swachh Bharat, Swasth Bharat, Innovate in India, Make in India, etc. And we all tend to laugh a bit at this and we say, oh, this is really silly, etc. It is a little bit irritating the way it's been formulated, perhaps by some of the governmental agencies. But I think it's important that, we do think about how our work can address societal needs. I think this is a personal decision each person has to make. And if you want to do string theory and that's what you're really good at, go ahead and do it. But in my case, I slowly changed I started out, initially wanting to do either high energy physics or astrophysics, and over time, slowly my interest changed and the direction of my research changed. And this is, again, a Lakshman cartoon where he said, I've made it in such a way that it will give 3.5 miles more for the same energy. So what did Gandhi have to say about this? This is a picture of Gandhi when he visited IISc in Bangalore. And he said to the students, unless all the discoveries that you make have the welfare of the poor as the end in view, all your workshops will be really better, no better than Satan's workshops. I mean, Gandhi really had a way with words, you have to say. Of course, I mean, this is going over the top, saying it's no better than Satan's workshops, but he did encourage people to work on topics keeping India's needs in view. And combating disease, I was happy to read that IIT Guwahati became the first institute to produce COVID-19 diagnostic kits. These are various newspaper headlines that I just pulled off the web, showing different ways that scientists in India have contributed to the COVID-19 situation to combat it. You know, diagnostic kits, ventilators, vaccines, masks, etc. So, and of course, directly there are people who are virologists, etc., who are working on it. What are the deadliest diseases in India? There are many diseases that affect our population, and certainly doctors work on it, but also medical researchers can work on it. And maybe even as physicists and chemists, we can contribute. For example, here you see that 519,000 deaths due to diarrhea. And diarrhea is often, of course, caused by impure water. And so here, for example, this is a project that was done in Professor Pradeep's department, in the chemistry department in IIT Madras, where they've been working on various projects to produce clean water. So this is a project which they call Vayu Jal, to produce water out of thin air. So we certainly can work on combating disease, even if we're physicists or chemists. This is a slide I took from a talk I chaired just 3 days ago by my friend Nicola Spalding, who's at ETH in Zurich. And she titled her talk, Finding Happiness and Saving the World Through Electronic Structure Calculations. I thought, well, this is, sort of a funny talk, and I wasn't sure how serious she was, but why did she talk about saving the world? She was talking about saving the world because what she was working on was the important challenge of water splitting. You all know, I'm sure, that we want to use hydrogen as the fuel of the future, because if you combust hydrogen, the only exhaust is water. But we don't have a good source of hydrogen, and currently most hydrogen is generated from natural gas, which is of course a fossil fuel. So we want a catalyst that will efficiently perform direct solar or electricity driven water splitting, and this is something that many physicists, chemists, material scientists, chemical engineers are working on. Another challenging problem is climate change. So carbon dioxide is, of course, a greenhouse gas, and it is causing global warming. So this chart shows how global temperatures are rising along with the rise in carbon dioxide. So there's a clear causal connection between the two. And many people are working on whether we can not only remove this carbon dioxide from the atmosphere, but convert it to something useful. So, for example, if you could convert it to methanol, so you can also make a lot of money if you do this. So these posters are from something called the X Prize, which offers $10 million to people who find a useful way to do this. And two of my colleagues at JNC, Professor Sebastian Peter and Professor Umesh Wagmare, were finalists in this competition. A really important issue is debates over agriculture, whether we should grow GM crops or not. This is something I think that's very important for India's future, and the debate is quite, I would say, unsettled as yet. And as scientists, we really can play an important role in settling this issue. So, a big thing I wanted to talk about, I really think we're not doing enough in this as scientists, though I'm very happy to hear about the outreach programs that Professor Subhradeep Ghosh mentioned at the beginning, because I think all this contributes to it. We have to foster rationalism and scientific temper and fight superstition, especially if it is harmful. So here again is a Lakshman cartoon where he's, these are three sadhus on their beds of nails, and for one of them they're saying, look how he's using the bed. I always thought he was the most scientifically minded among us. So I think we have a really remarkable statement in the Constitution, which says that it shall be the duty of every citizen of India to develop the scientific temper, humanism, and the spirit of inquiry and reform. I think, very, very few constitutions have a statement like this, and I think it's something to be very proud of. So science versus superstition. So science, I took out the dictionary definition. Science is knowledge about or study of the natural world based on facts learned through experiments and observation, whereas superstition is a belief or way of behaving that is based on fear of the unknown and faith in magic or luck. Okay, so if you look at these two definitions, you would say these two should be completely opposites, because science is based on the natural world and superstition is based on the supernatural world. And so you would think these two should always be complete opposites. But maybe the situation is not quite so black and white as I've shown in these two arrows. There are some gray areas which I will discuss. I do want to make clear that it's very important that when we combat superstition, we make the distinction between combating superstition versus combating religion. I think it's also very important to recognize that our constitution gives us freedom. It's a secular country. We have freedom of religion. Sometimes, if you look at certain practices, it may be hard to say, okay, is that a superstitious practice or is it a religious practice? But we have to be very careful to make that distinction and not infringe on religious freedoms. Again, now in coronavirus times, we are seeing so many superstitious and irrational beliefs. Okay, so one thing that was, really very strong at the beginning of the coronavirus outbreak was this thing that it was all caused by 5G. Okay, so I mean, this is some wall painting, wall graffiti about it, and this kind of this was a tweet that I've put at the bottom, and I certainly received lots of WhatsApp forwards from my friends at the beginning of the coronavirus outbreak, movies saying that it's all due to 5G, asking me what did I think as a physicist, should they believe it or not. I'm sure many of you face the same thing. And there are also many rumors about how to prevent coronavirus, how to cure coronavirus, okay, if you drink hot water, you won't get it. If you gargle with salt water vinegar, you won't get coronavirus. If you have coronavirus, if you eat mangoes, it will cure it. The thing on the right is a advisory put up put out by the WHO saying it won't cure you, but it's probably good for your health to eat mangoes anyway. Now, some of these superstitions are harmless, like it's not going to harm you probably to gargle with salt water or eat mangoes. But if you're going to do this instead of wearing a mask, or instead of social distancing, or instead of getting yourself admitted to the hospital once you contract coronavirus, that's when it becomes really dangerous. Then, even our Ayush ministry has been promoting various remedies for coronavirus. And so this is an advertisement online to buy a herbal mixture, which it says will prevent you getting coronavirus. And I'm sure traditional herbal remedies have some value to them. They probably do boost your immunity, but again, you have to be careful about exactly what you're promoting and what you're claiming for it. And I said in the beginning about Gandhi and earthquakes, and again, that topic has cropped up a lot again on Facebook and other social media. This theory has been around for a long time and it keeps cropping up again. There are certain people in India who have this theory that earthquakes are due to pain waves from dying animals. Okay, so this was a news item. And okay, so I thought I had another slide on it, but it seems to have disappeared. Oh, here it is. The order got mixed up here. So this is a long excerpt on it. It's saying, I'll read it for you. It says, the devastating calamity of earthquake happens due to collective slaughter of living creature. I blacked out the name of the person because I did not want to make fun of somebody who is a scientist from a leading university. But, what he's saying is a bit worrisome. He said that it's presented in Russia and that it's nullified all the theories regarding earthquake. And it also says it substantiates Einstein's pain wave theory. Okay, now they always want to bring in Einstein's name. And I'm pretty sure Einstein had no pain wave theory. And it says they control, you can control radio and TV and satellites, and you can get dust from the moon to the earth using these pain waves, etc. Superstition, again, fear of vaccines. A lot of people are worried about the COVID vaccines right now. This is a protest in Mumbai against, lockdowns, vaccines, masks, 5G, RFID chips, etc. So people are protesting these things. Another thing that's really cropping up again, more in the West than in India, and it seems absurd to us, but people are really believing this. There's a increasing number of people who refuse to believe that the earth is round, and they insist that it's a flat earth. 10% of Americans don't believe that the moon landing was real. So why, you may say that the difference between science and superstition is science, everything is demonstrated and proved, whereas superstition is all on belief. But it's not so clear-cut, because if I ask myself, do I believe in the general theory of relativity? Yes, I do believe in it, but I have never taken a course in general relativity. I have not read Misner, Thorne and Wheeler. I did not see the experiment performed where, the light from a star was bent by the sun, etc. So I believe in it because people I trust tell me that general relativity is correct. And this is the same for superstition also, right? People believe in certain things because someone they trust tells them. I think the difference is that if I wanted to do these experiments, I could do it. If I wanted to work my way through Misner, Thorne, and Wheeler, I could do it, I believe. And in science, if you want to falsify something, then there are clearly laid out protocols how you disprove something. Why do people have irrational beliefs? I think they have fear of the unknown, the urge to accept simple and simplistic explanations, difficulty comprehending scientific concepts and statistics, suspicion of authorities, suspicion of scientists. And we as scientists don't make enough of an effort to reach out and communicate. Okay, like in coronavirus, people are seeing graphs like this, and it's hard even for me to understand what this graph is saying. So it's not very surprising that somebody else, an ordinary person says, I don't understand, and then it's much easier to just believe everything is due to 5G. Why don't we as scientists generally speak out? We feel our time can best be utilized by concentrating on our scientific work. We're reluctant to get involved in controversies. We're afraid of upsetting people. We're afraid of being misunderstood. And it requires moving out of our comfort zones. We ourselves are sometimes superstitious. Like there's this famous story about Niels Bohr, that somebody went to see him in his country house and they saw a horseshoe hanging there. There's the superstition that horseshoes are lucky. And someone said to him, surely you don't believe that horseshoes are lucky. And he replied saying, no, of course I don't, but I'm told that it works even if you don't believe in it. So, for me, when I started my new job in India, I was supposed to start on October 1st, 1996, and my grandmother told me, oh, you should not start on that day. It's a Tuesday. It's very unlucky to start anything on a Tuesday. And I sort of quarreled with her and said, no, I'm a scientist. I don't believe in all this. And then when I called up the institute and said, I'm coming on October 1st, the administrative officer I talked to said, madam, well, it's a Tuesday. Can you come one day earlier or one day later? And, that's, I don't know if you call that an auspicious beginning or an inauspicious beginning. Here is a list of ISRO's PSLV launches. I'm going a bit fast because I'm pretty much out of time. So you may not have time to look carefully at this list, but what is funny about this list is if you look at the PSLV launches, they're all numbered. And if you see, we had 11, we had a 12, then we jumped to 14 and 15. Okay, there was no C13 because presumably 13 is an unlucky number. We do Bhumi Pujas for our scientific institutions. I don't know how to think about it. You can say it's a nice tradition, or you can say it's a superstition. Various scientists were surveyed, and if you look at the percentage who believe in various superstitions, so-called, about 15% believed in astrology, 15% believed in Vastu, 17% believed in faith healing, higher and higher percentages believed in miracles, homeopathy, about half of them believed in homeopathy. So I'm almost at the end. So Nehru, on the social responsibility of scientists, he said, too many scientists today who swear by science forget all about it outside their particular spheres. The scientific approach and temper are or should be a way of life, a process of thinking, a method of acting and associating with our fellow men. Contributing to discussions about equity, this is a picture of the top science administrators in India, the president, the Minister for Science and Technology, secretaries of DST, DBT, directors of the IITs, ISERs. Do you find anything strange about this picture? As soon as I saw it, I noticed something, which is there isn't a single woman there. So something's really wrong. So India's R&D sector is disproportionately populated by males from privileged backgrounds. Only 13.9% of our researchers are women. which it may come as a shock to you. It came as a shock to me, which is we have the second lowest fraction of women researchers in Asia and the sixth lowest in the world. And similarly, the castes are unevenly represented. So this shows the caste distribution amongst the faculty at one of the IITs, and you see that the disadvantaged castes are have a very low representation. And we do need to worry about this as a scientific community. We need to become more diverse and more inclusive. And people are increasingly trying to use science to justify inequity. You know, there's these things of race science and gender science, and people will say, oh, if you do a fMRI, you will see men's brains are different from women's brains. And, you know, people are trying to do these genetic studies of castes, etc. And I think we have to be very, very careful about all this, very cautious. These are very complex issues, and we really have to be very vigilant that people don't try to misuse science to justify inequity. There are new developments in Indian science administration and funding, which is the STIP and the NRF. I don't have time to talk about this. I'm just mentioning that they exist. To end, I just wanted to end on a light-hearted note. So I ended with this picture of Einstein riding a bicycle, and he said, life is like riding a bicycle. To keep your balance, you must keep moving. Thank you very much, and I'm sorry I went a little bit over time. Thank you.
Thank you, Professor Opana. It's a wonderful talk, and thank you for sharing your views on many aspects of the science and society in India, and also you touched upon many things which is relevant in the global this one. I'm sure it opens the debate, and then many of our colleagues and then friends would be kind of have questions, will have questions, and so let's open the discussion. I don't see any, hands. We can just speak out also without this thing. Okay. So
okay. I'm a bit relieved. I was a bit scared of questions.
I had a kind of some, not really questions. I mean, one question was, okay, maybe let me put the question first. The statistics when you showed this one, no, in the caste and then the ratio of the people in this thing, how was it done? Just a curiosity, okay, nothing other than that. Was it actually normalized to the population also, or is it just the number of people?
No, it is just the number. It was the number of faculty at one of the IITs, their caste backgrounds.
Maybe the correct statistics would be to take the ratio or normalize it with this one. I'm not saying that it is. Even then, you will really see
if you see it, I think it will look even worse, actually.
Yeah. Maybe, yes, yeah.
Yes, I believe so.
Yeah, I kind of liked many things that you said, almost everything that you said, but specifically on the scientific temper that we have, I think we certainly should do something as a scientific community. Not many people do that kind of thing, maybe because of the lack of the time, or at least that's what we think, that we have to spend some time doing that.
Yeah,
but it is important. I fully agree with that.
I went a bit fast through that part of my talk because I felt I was running out of time, but I really think it's very important. I really think we don't do enough to reach out to the public at large and speak up about things. I mean, like say this news item comes out that earthquakes are brought about by pain waves due to animal slaughter. Amongst ourselves, we may all say, oh, how ridiculous, we laugh, we'll send WhatsApp messages, but we don't go and speak out to the media and say, look, this is nonsense. Einstein did not have a theory of pain waves. There is nothing called pain waves. Maybe we are scared. Maybe we don't want to get involved. We are worried that we will be attacked. But if we don't speak up, then these things will persist.
Yes, that's right. I fully agree with that. Yeah, Subradev, please.
Yeah, I just have a comment to add, Shobana. I think simultaneously with this, there should be a concerted effort because India is a diverse country for the scientists to reach out to general people. I mean, the general people can be our mothers, grandmothers also, to talk about, vernacular medium, through vernacular medium, it's a community outreach to talk about, scientific topics in a very layman's language. I tell you my personal experience. One of my colleagues, Shubhaditya Bhattacharya, he has been instrumental in setting up a program called Science for All. So it's a community radio station started once again by a sort of former physicist who was my junior in Shubhaditya's batchmate in Jadavpur University. I mean, she actually is an activist on various things in Calcutta. During the lockdown, they started this community radio station, and around July, it was Shubhaditya's brainchild that this Science for All. So it is basically discussions in Bengali. It's a interview kind of thing, and it does not have to be a very quote unquote eminent scientist. It can be a postdoc also who is who can speak well and communicate well. So topic starting from the fundamentals of high energy physics to turbulence, to about COVID vaccines, to antibiotics, the science of antibiotics, the science of the glaciers in the context of this recent Uttarakhand thing. Those are being covered, and it has become immensely popular. That people are writing in their pages, and they are basically sending, requests about, sort of expanding it. So I would say that if we are serious about it, and there are several students, from various linguistic backgrounds, if they can think about this thing, that to start this kind of community outreach, a simple interview kind of thing in the local language, which is accessible to many, particularly people in your household who generally apparently are not very interested in science, but maybe it may trigger things. I think that will have a quite a significant outreach.
Yeah, and I mean, so many little things, like when the LHC was going to be turned on, this rumor spread that the world is going to end because a black hole is going to be created. I mean, LHC means Large Hadron Collider. And so many people phoned me to ask, Shobna, you're a physicist, is it true the world is going to end tomorrow? And these kinds of things, these are opportunities where we should really seize to really educate people about what science is and what physics is, etc.
Yeah, that's right. Anybody else? Others? Okay, just since until somebody comes up, just let me take another like what in the line of what Subradev was telling, and also maybe individually we can all do these various different things, but perhaps I don't know what are the efforts from some of our scientific bodies, like say National Academy of Science or physics education. I mean,
I'm going to say that the academy should speak up more than they have been doing on these matters, because that also gives us a little bit of, it gives you stronger voice, and it also gives protection to individual scientists who may be worried that they will be targeted. I mean, recently, the academy spoke up about this thing about you have to get clearance from the ministry to have foreign speakers in online conferences. I mean, it's good they spoke up, but this is something, a very niche area which only affects the working lives of scientists directly. They should speak up more on societal matters.
All right. And just another thing about this, since you were talking about this scientific advancement in India, what future directions one could go, no? India certainly has a great advantage of the younger population, which stands at something like 50% of our population is close to 25 or less than 25. Okay, whereas the world average is 38, the European average is 40 plus, etc. So now that's one thing. The other thing is the policies that matters. You mentioned Nehru, who clearly had a scientific temper and then wanted the society to have that, and then and many other, almost all our people at that time. I am not sure about Gandhi's exact views, as you said, but for him, so the constitution also has spelled it out very clearly in that. And some of the policies, Nehruvian policy, for example, starting IITs was one of those things. And even now we do have policies. We have the Make in India. I mean, it's kind of certainly, it's not spelling out exactly how to go about, but that is encouraging people. And then I'm sure many people, many small, these things have come up in the science and technology. But I think policies do matter, and then maybe it's one of the things that we have not really woken up to is the future. So we still really have a short term this one, like we don't really know what we may have to look for after 5 years or 10 years or something like that. Whereas China, just to give an example, China has been spending so much they were investing not only the money and manpower, everything, in one area which is artificial intelligence, which certainly, in my personal opinion, and I think from opinion of many people, is one of the things that's going to actually take the society leap to completely a different level, maybe in 50 years. But I don't know what's our investment in that, and things like that. So the modern view, and then understanding how exactly what should we do, etc. You did not really comment on those things.
So I deliberately left out government policies because I thought they were too controversial an area. But I think the advantage China has, and of course it's I say advantage in quotes, is that their governments do not have to worry about being re-elected in a few years, so they can implement policies without worrying about catering to the popular perception. It seems to me our governments, they are always thinking about what will appeal to the vote bank. And also, I have seen that many of the policies we have in India, I think, are quite good, but they are not implemented well or enforced well. And it seems to me that people are more interested in starting flashy new programs than ensuring that existing programs are implemented. By the way, somebody has their hand raised.
But I was wondering, who is it? You can speak out.
Yeah. So it is me. Can you hear me?
Yeah.
Yeah, I have a short observation. See, it is my opinion that if we want to see that science really plays a key role in shaping the future of India, I think one part probably that is often neglected is the education, is the syllabus part of primary school, maybe up to class 10. So this part is totally neglected. Neglected means, parents are taking due care, teachers are taking due care that syllabus is to be covered. So the emphasis is on the syllabus or the bookish knowledge. So I think if the attempt is made that the scientific temper is developed during this period itself, because my feeling is that scientific temper cannot be like, just few years of education in physics will allow somebody to, grow the true scientific temper. So, too much of emphasis on covering the syllabus, not only during the first few years, but even later also, I think that is really killing the true scientific temper. So probably we should also look at how the child are to be educated in the very beginning.
No, I agree completely. I was visiting a friend's house in Germany a couple of years ago, and her daughter was, she had a physics lab report to write, and she asked me if I could help her with it. And I was completely amazed how different it was. She was, in whatever, 8th standard or something. But she had to do an experiment and she was expected to design the experiment herself. She had to say what were the dependent variables, she had to say what were the independent variables. If her experiment didn't work, she had to write the reasons why she thought it didn't work. All this, and this is starting already at 8th standard. And then I think if you have that kind of training at that level, it's not surprising that they produce very good scientists.
True. I think now maybe we are kind of getting a little late. So is there any other urgent question or any comment or anything? Otherwise, okay. I don't see any hands. Okay. Otherwise, thank you, Professor Shobhana, for a wonderful discussion, sharing all your views on various aspects and joining us this morning. Thank you very much.
Thank you.
So over to Angana.
Thank you, sir, and thank you, ma'am, for the very interesting talk. Now I request Dr. Ashwini Kumar Sharma to please take over the session as the session chair for the second part.
Yeah, so I hope all of you can hear me. So thank you very much, Angana, and it was a wonderful presentation by Professor Narasimhan. So let us now come over to IIT Guwahati. So the theme of this year's National Science Day is Future of Science, Technology and Innovation, Impacts on Education, Skill and Work. And I believe that there cannot be a more ideal day than today to celebrate the achievements of our own faculty members and students. So today we have two talks in this session. So let me first introduce you to our first speaker, Professor Basant Ranjan Barua. So Professor Barua is an experimentalist in the laser and photonics group in our department. He obtained his PhD from Imperial College London. His basic research areas includes programmable diffractive optics, confocal and super resolution microscopy, wavefront sensing, etc. Professor Barua recently, in the past few years, he also worked on the, where one can think about, experiments and the methodology to transfer the data. Okay, what we have known is that, a few years back, we were looking at fiber cables for the transmission of data, but there has been quite a lot of work going on in a different way where can the fiber optic cables be avoided and can one have transmission of these data through air or any other medium, but not necessarily fibers. So it is in this sense that Professor Barua and one of his graduate student, Shantanu Kanwar, who were awarded a US patent, which was based on free space optical communication system apparatus and related methodology. So today, Professor Barua is going to present his work as a bit extension of this work as well. The title of his talk is Robust to Free Space Optical Communication Using Orthogonal Aberration Modes. So now I request Professor Barua to please share his work with us. Thank you.
Okay, good morning, everyone. First of all, can you hear my voice and can you see my screen?
Yes.
Okay. So thank you, Ashwini, for the nice introduction, and thanks to the HOD and the organizers of this National Science Day in our department for giving me the opportunity to talk about some of our work, of the group's work in last few years. So what I'm going to speak on today is the development of a robust free space optical communication system using orthogonal aberration modes. And as you can see in the sketch, which is on the screen, you have a sender who is on probably one building, it can be one mountain maybe, and he is sending information to another receiver who may be on another building or another mountain. And the information is not going through any wave guide or any cable. It is passing through free space. And the free space may be air with certain amount of turbulence. So what we demonstrated is a certain way of sending the information using the property of the light beam without getting the detrimental effect of the atmospheric turbulence. So before I start, here is the disclaimer. Although most of the results that I'm going to show are our own result, but in order to explain the principle and the importance, I may use some results and images which are not of my own, of my group's own result. I'll start with a tribute to the effect, and I'm just revisiting some 93 years back when Raman and Krishnan, they were finalizing the results of their famous experiment. And in that experiment, what they have seen, it is now surprising to know that actually their first few experiments were using sunlight. So they allowed sunlight to pass through a liquid, and then they try to detect the wavelength, and they notice that there is a certain shift in the wavelength. And what we know now, that this shift in the wavelength is a signature of the energy levels of the molecules which constitute the liquid. So it was more or less kind of a wavelength modulation by the molecule, and the information of the molecule is carried by the scattered light, and the part of the scattered light can be detected, and we know about what is there in the molecule or what is the property of the molecule. So it was 1927 that Krishnan started more seriously about the experiment. He initially used sunlight, then he used a spectrograph, and later on he replaced sunlight with the mercury lamp, and with a very simple setup, which you know, there are number of stories like how cheap that instrument was, but whatever, it was a great discovery which was published in Nature in March 1928, and today we are celebrating that particular spirit of Krishnan and Raman with our, as a cell has developed. So probably the first use of light as an information carrier was the time when the caveman was probably waving his hand, and he was trying to pass on an information to another person at some distance away. Now, if we analyze this particular demonstration, probably the sunlight was the source of light which fall on the caveman, and he was the transmitter who is transmitting a certain information by waving his hand. So his hand becomes an intensity modulation, an intensity modulator of the light beam. And this light beam, which is scattered by his hand, carrying the information about whatever he wanted to convey, has traveled a certain distance of air, and it reaches the other person's eye, and the eye of the other person has become the receiver. So you see, this free space optical communication system was probably there even it has been there for time immemorial. But what I am going to talk about is using the other property of light beam as a information carrier, and the property of the light beam is related to the phase of the light beam. So we know that light is an electromagnetic wave with amplitude and phase part, and this phase part, if you consider the beam as a whole, can also be defined as a wavefront. when we want to define a wavefront, we can call the wavefront as a loci of points having the same phase. So if you join points having the same phase, then it becomes a wavefront. And if the relative phase is represented by a 2D mathematical function, then that becomes the mathematical representation of the wavefront. It can be path difference. It is a path difference function multiplied by what is called the wave number, or 2 pi by lambda. So that is mathematically how wavefront can be defined. And in ray optics, if we want to define what is a wavefront, then we know that you have to draw perpendiculars to the rays, then that becomes a wavefront. Now in this particular diagram, you can see there is a plane wavefront, there are non-planar wavefront, then there is a convex wavefront, and there is a concave wavefront. So there can be a beam of light with a certain amplitude, but it can have different wavefronts. Now this wavefront can be used to transfer the information. And the first attempt to use the wavefront of light to carry the information was first proposed by Gibson in 2004. And what he proposed was a wavefront, a special type of a wavefront, which is also called helical light beam or orbital angular momentum mode. So what is orbital angular momentum mode? If you consider the beam that is coming out of a laser, it has a plane wavefront. So phase is everywhere is constant. And when you focus this beam, you get a intensity distribution where the maximum intensity is at the center. And this is popularly, it can be called as an Airy pattern. And then you can see the false color image on the right hand side. Here it is showing the same color, means the phase everywhere is 0 or phase everywhere is constant. However, if you think of a light beam where the phase is increasing from 0 to 2 pi or 0 to minus 2 pi, then this becomes a helical beam or a vortex beam, and this kind of a beam will carry orbital angular momentum. So the leftmost column, you can see the graphical representation of the wavefront, and then the middle column, you can see the intensity distribution. Now, when the beam carries orbital angular momentum, the intensity is no longer having a maximum at the center. It is having a donut kind of a shape. So there is also intensity modulation. Now, the phase can be varying from 0 to 4 pi, or in general, the phase can be varying along the azimuthal angle from 0 to n into 2 pi, where n is an integer. So that way you can have different orbital angular momentum modes, and normally m is the index which is used to denote what is the orbital angular momentum mode. For example, m equal to 0, 1, 2, 3, and so on. And it so happens this orbital angular momentum mode is a subset of a solution of the paraxial wave equation, and the solution is called Legere-Gaussian beam, Legere-Gaussian mode. So this orbital angular momentum mode is a subset of the Legere-Gaussian mode, if I want to define it mathematically. Now you see, when you have a beam, the beam can have different m value or different orbital angular momentum, where orbital angular momentum is given as mh cross. So the beam can be there, but the beam can carry different orbital angular momentum. So the information can not only be carried whether by the presence or absence of the beam, but while the beam is present or while the beam is on, while the laser is on, we can keep the laser on, and we can modulate the phase profile. We can change the phase profile. We can increase the m value. We can change the m value from 0 to 1, 1 to 2, 2 to 3. So the information can in fact be carried in terms of the m values also. So this was what was proposed in 2004, and here comes the question: how can you generate this kind of a helical beam or this kind of a orbital angular momentum mode? The simplest way of creating such helical beam or orbital angular momentum mode is to pass the laser beam through a spiral phase plate. So you have to carefully select the height edge of the spiral phase plate. But in principle, if you choose the height carefully with an appropriate refractive index, as the beam passes through, the beam will carry the helical phase profile, or it will have orbital angular momentum of a certain index. But instead of generating a helical beam or a beam with a fixed orbital angular momentum value, you can also have some flexibility by incorporating dynamic hologram method. So in dynamic hologram method, basically it's kind of a grating, but this grating can be reconfigured in real time, and this particular grating will diffract light, and one of the diffracted beam will carry the phase profile of the orbital angular momentum mode. And the key point here is how to calculate the grating. In short, this grating is nothing but the interference pattern between a plane wave and the wave that you want to generate in the diffracted beam. So this particular technique is also called computer generated holography. Now, if you can generate this kind of an orbital angular momentum mode, and the beam carrying orbital angular momentum mode is carrying the information, but when it reaches the receiver, one has to also detect the presence or absence of the orbital angular momentum modes. And the way how to detect the presence or absence of the mode is to incident the beam carrying orbital angular momentum again on a hologram or on a grating. And you see this is a fork type of a grating. This is to detect the beam carrying orbital angular momentum mode with index equal to 1 or -1. Now what happens if the beam is having a certain orbital angular momentum m equal to 1, then the grating will lead to diffraction, diffracted beam, and the +1 order diffracted beam will have maximum intensity at the center if the beam has got orbital angular momentum of index 1. And if the beam has got orbital angular momentum of index -1, then the -1 diffracted order will have maximum intensity at the center. But let us say the incident beam has got index m equal to 2, and you have a fork to detect orbital angular momentum of index 1 or -1, then in none of the order you will have maximum intensity at the center. So this way, by looking at the presence or absence of maximum intensity at the center, it is possible to detect whether in the incident beam orbital angular momentums are there or not. And using the property, whatever we have discussed just now, free space optical communication systems have been developed. So in free space optical communication system, there are several channels. Normally what happens when we send information through an optical fiber cable, it is mostly intensity modulation. So there is light or no light. Light is considered as number 1 and no light is considered as number 0. In this case also, every channel will have light or no light, but different channels will carry different orbital angular momentum. And they are combined by using beam splitters. Eventually you combine all the channels to eventually to one beam, which will be traveling through free space. And then at the receiver, you again separate the beam into different channels, and then light from the different channels will be incident on the fork hologram that I showed in the previous slide to see whether a particular aberration, a particular orbital angular momentum is present or not. So this way, instead of having just one way of sending information by light or no light, you can now have increase the information content of the beam by several times by using different orbital angular momentum mode. And this can also be combined with wavelength division multiplexing, where you are not only changing the orbital angular momentum index of the beam, you are also changing, you are also using different wavelengths and combining them before sending through free space. And using this, it was shown that one can have a speed of information content of about 100 terabits per second. And experiments were conducted where information, of course, not necessarily at this highest information content, but in principle, it was shown that the information can be carried up to a distance of 3 kilometers. But there lies some very serious issues with the orbital angular momentum based communication. The most important issue is that, as you can see, that this different orbital angular momentum mode has got different intensity profile. So here you can see L equal to 0. Of course, in previous slide I use I use M instead of L, but this is L. Here is the index of the orbital angular momentum. So different index will have different intensity profile. Now, if you are using different orbital angular momentum to carry the information, now to transfer different information, you may have to switch from one mode to the other. But when you switch from one mode to the other, at a particular location in the beam, there is a perceptible change in the energy distribution or intensity distribution. And it is well known that one can very easily detect or measure a change in intensity or change in energy. Especially if you compare the change in the phase profile itself. So change in the phase profile may not be so easy to detect, but change in the intensity distribution is easy to detect. So therefore, this kind of a mechanism is not totally free of eavesdropping. Then you have seen that different channels are combined using beam splitters, which which significantly puts a constraint on the flexibility of the particular mode. And orbital angular momentums are severely distorted by turbulence. They have a very severe effect of turbulence. So turbulence has always been a big issue as far as free space communication using OM mode is concerned. But the most fundamental issue with the orbital angular momentum mode is that these modes do not form a complete basis set. And since they do not form a complete basis set, they cannot provide optimal information content. And because of the same reason, the particular mechanism do not have an inherent way of taking care of the effect of turbulence. And you need a separate sensor to do that. So what we proposed is that in order to take care of the issues with the orbital angular momentum, one can instead use aberration mode, which is known as Zernike modes. Now, these Zernike modes mathematically are functions which are orthogonal to one another, and they form a complete basis set. And using holographic means or using some special phase modulator, you can generate a single Zernike mode, or you can generate a combination of modes. But one thing you have to keep in mind is that here we are only modulating the phase part of the beam. So the amplitude part more or less remains unaffected. Only the phase part is modulated. So when we switch from one mode to the other, the energy distribution more or less remains unchanged. And the basic system to use Zernike mode to carry the information from one place to the other, we submitted for a patent, and it was granted in June last year. But here comes one important question. If you want to send information from one place to the other by using Zernike mode, then you should be able to measure the strength of Zernike mode. And you are not necessarily using just one mode, you will be using a linear combination of mode, and each mode can have multiple strength, different strength. So we should be able to measure them simultaneously. So in this regard, we proposed about a year back a kind of a wavefront sensor that uses binary hologram. Light beam carrying different mode is incident on the binary hologram, and they diffract light, which can be captured with a camera. You can see in the figure B, and you can analyze these light spots to measure the strength of different Zernike modes simultaneously. For example, here you can see I am using 3 Zernike modes with different strength. Type A, type B are the conventional sensor, and type K is our sensor. So our sensor can very efficiently detect the presence of aberration and without getting the effect, what is known as crosstalk effect. Crosstalk is the effect when the presence of one aberration mode is affected by the presence of some other aberration mode. So this is what our scheme in a block diagram. There is a laser beam, and the laser beam is modulated by using the user information. And for this purpose, we use a dynamic hologram or a dynamic phase modulator. Then the laser beam carrying the phase information is passing through the free space, and then the beam is incident on a hologram. Then the hologram diffracts light, and the diffracted light is captured with a camera, and which is analyzed to decode the information. What we demonstrated is that you can use one Zernike mode, but the Zernike mode can have 5 different strengths. So we are using one mode with 5 different strength or magnitude of the phase part, or 2 modes with 3 different amplitude of the phase, or 2 modes with 5 different amplitude. So all these different schemes will have different information carrying capability, and we are calling them base 5, base 9, base 25, and so on. And here I am showing how we can use base 9. So as you can see, base 9 means we are using 2 Zernike modes, with each Zernike mode having 3 strengths. Now let us consider that we want to send the information which is in the form of a number 200. So number 200 in the decimal form, and we are using base 9. So we have to convert to base 9. We convert number 200 to base 9. In base 9, 200 becomes 242. Now this number 2 should be represented by a unique wavefront, and that unique wavefront is a combination of the wavefront carrying Zernike mode Z6 and Z11. These are 2 different Zernike modes. So 0 amount of Z6 and minus 0.5 amount of Z11 gives me 1 unique wavefront, and 0.5 of Z6 and 0.5 of Z11 gives me another unique wavefront. So I am calling the first unique wavefront as 2, the second unique wavefront as 4, and our dynamic phase modulating device will create these 3 wavefronts consecutively, sequentially, and they will be passing through the free space. Now, when it reaches the detector, they will be incident on the binary hologram, which will be simultaneously measuring the strength of both the modes. And when we measure it, it will give me some sensor output, and that need to be thresholded properly so that the proper strength can be evaluated. And once we find out the proper strength, we get the number in the base 9 format. From base 9, we convert it to base 10, which is the number 200. But still we have not figured out, we have not answered the fundamental problem, is the compensation of the atmospheric turbulence. So since any free space communication system may have to travel through the outside medium where the effect of turbulence will very much be there. Now how to compensate for the effect of turbulence? So what we propose that the wavefront, information carrying wavefront, will be followed by a reference wavefront. So this reference wavefront will not carry any information. It is a plain wavefront from the transmitter. But as it passes through the atmosphere, it will pick up the atmospheric effect, and it will be converted to some arbitrary phase profile. Here we make use of the property of the aberration mode or the Zernike mode, that they form a complete basis set. So the reference wavefront that has picked up the effect of turbulence is decomposed into Zernike modes. And once we find out what is the composition in terms of Zernike mode due to turbulence, then their effect on the information carrying wavefront can be obtained by simply performing a subtraction operation, where you can see Sk is the output, sensor output or transmitter output for the information frame, and we subtract it from the result of the reference frame. Here you can see these are experimental images of the focal spot pattern or diffraction pattern. And we performed the experiment in the laboratory environment, where we performed the modulation using spatial light modulator, and then they travel through a distance of 2.4 meter, and then it reaches the transmitter. Here we have used a fan, a pedestal fan, and we created turbulence using the pedestal fan. And in the demonstration part, you can see when there is no turbulence compensation, even if we are sending a fixed amount of Zernike mode, their strength is really changing. And when we switch on the turbulence compensation, the strength becomes steady. And these results we recently published in Communication Physics. And these are some more experimental results. Instead of sending numbers, we send an image which passes through this turbulent atmosphere, and of course, artificially create a turbulent atmosphere. And if we do not use our compensation scheme, then there is, you see, if we do not use compensation scheme, then there is distortion in the received image. But once we switch on the turbulence compensation, the distortion is removed. So to summarize, light can act as a carrier of various information. To start with, we have seen that light carries the information of the molecule, energy level of the molecule, and it has been used for long distance communication from time immemorial. And light-based optical communication system have been developed using orbital angular momentum mode. However, they have certain issues, especially they are susceptible to turbulence and eavesdropping. And more importantly, since they do not form a complete basis set, they will not provide the optimal information constant. So what we propose is a Zernike mode-based communication system, which has inherent security against eavesdropping, because there is no fluctuation in energy when we switch from one mode to the other. And due to the completeness property, it has an inherent capability of compensate for the effect of turbulence. So with this, I will be ending here, and thank you for your patience.
Yeah, thank you very much, Bakanta, for a very nice and very lucid and simple presentation. So now I welcome questions from the audience, please. Yes, Paulus, please go ahead.
Yeah, Basanta, thank you for a very interesting talk. And I have a quick question. And one is the fan, the experiment that you were talking about, no? The fan, the compensation is not tuned to the fan kind of this one, right? Like it could be any. Say for example, when you use the fan, it may be some particular speed, varying speeds, or kind of thing is also tested or no?
Yeah, varying speed is tested, but what we looked at is the effect on the Strel ratio. See, like how much is the effect of turbulence technically is defined by a degradation of the peak intensity, which is called the degradation of the Strel ratio. And what we found, because the fan actually creates not only a wind, it creates a whirlpool, or it creates really turbulence. And due to this, there is a severe degradation in the Strel ratio. So for example, if you consider a normal light beam has peak intensity equal to 1, when you have turbulence with a fan, in our case, it degraded to 0.3. So there is a 70% degradation, which I think is much higher than the degradation that you will see even if you are considering outside atmosphere. Of course, I am not claiming that we have already tested the severe amount of turbulence, but it is quite a significant amount of turbulence that we have tested. Only thing is that the distance it has traveled is not significant. So in our next phase, we want to increase it to maybe some kilometers. Okay. But free space communication systems right now, whatever you have seen, the demonstration of 100 terabits per second, this demonstration was for a distance of 1 meter. So these are all basically demonstration in the laboratory environment. So most of these demonstrations are in laboratory environment, but we can claim that we have introduced, although the turbulence was introduced by a fan, but the degradation on the beam is quite significant in terms of the degradation in the Strel ratio.
Okay, the other thing is there are also other factors than, apart from the turbulence itself. No, so for example, humidity and absorption by various these things, etc.
Yeah.
to, yeah, so those things.
Yeah, that is, yes. So, yeah, so this is what the property of the, this is where does the property of the Zernike mode comes into play. See, these Zernike modes, of course, up to a certain limit, they are completely orthogonal and they form a complete basis set. Now, it doesn't matter whether the distortion in the transmitted wavefront is coming due to atmospheric turbulence or due to a variation in humidity. Eventually, the information content is affected due to the distortion in the phase profile. Now, in this case, in this particular mechanism, it is not important to us about the cause. If the rate of change of distortions, variation in the distortion in the phase profile is within the limit, then irrespective of the cause, our scheme should be able to compensate for the turbulence, for the effect in the distortion. Okay, because eventually we look at the phase profile at the receiver, and we decompose it in terms of the individual modes. And once we decompose the strength of the individual modes, they are subtracted from the signal to get the correct signal.
Just a quick last question. Just instead of using this open communication, is it not possible at all to use, say, for example, cable or some such as thing? I mean, for the helical beams.
Helical beam is, I think, there are some demonstration that they maintain the orbital angular momentum profile to a certain extent even they travel through, let's say, optical fiber cable. But all sorts of other spatial light modes is, I mean, the phase profile may not be maintained when they travel other than through free space. So I think orbital angular momentum is demonstrated to be capable of traveling, but other modes probably still it will be some time before we see a possibility of transmission through cables.
Okay, thanks. Yeah.
Okay, so any other question? Anything that anyone, so students especially, you can also ask some very basic things if you have not understood. So I think that is also very much welcome. Anyone? So, okay, Basant, I just have a question. It's more from, its applicability point of view. So what is the, current status? You have discussed what are the other methods which are available, which, which can compete with what you have mentioned about. So do you have any idea, or would you like to elaborate on that? So is this the only way to achieve this free space communication, or there are other methods also? And what advantage or disadvantage do you see compared to what you have done?
See, as far as free space communication system is concerned, their inherent advantage is the information content. If you put them in a waveguide or optical fiber cable, then they will depend on the property of the medium, and then it will limit the information content. So right now, the attempt is not to go for the cable communication, because there are other things also, like, for example, if you want to have a earth to satellite communication, you cannot really think of a cable-based communication system. That has to be free space communication only. So these free space communication system are also aimed at, maybe communication between two mountains. So you have a receiver and transmitter, two mountains, several kilometers apart. You don't need any other infrastructure. Just put the two systems, and then you start communicating, or you communicate to a satellite. So that is why I think right now the advantage of free space communication with respect to cable communication is quite obvious. Of course, I'm not saying that it will altogether replace cable communication. So cable communication probably will be there for conventional purposes, but for other purposes where free space communication have obvious advantage, I think that is quite well known. But as far as other competing method is concerned, see, right now 90% of the free space optical communication system uses orbital angular momentum mode, And these are all mostly laboratory systems. So nobody has so far developed the realistic system because of the main problem, the effect of turbulence, how to compensate for the effect of turbulence. So because of this, still, commercial system is yet to be developed. But I think, that is not surprising also. Anything will take several decades before it is commercialized. So this was proposed in 2004 that orbital angular momentum can be used for free space communication. And maybe after 5-6 years after, people started working. And now there are a lot of work, but most of the works are using orbital angular momentum mode. And if you just look at my paper, we first proposed that a different type of a orthogonal aberration mode can also be used. And we really had a hard time with the reviewers, with the editors, to convince them that yes, this works. And so we have to send several experimental results, and we have to argue a lot to convince them. So there are most of the people are follower or are believer of orbital angular momentum mode. So they are the main competitor with whatever we are proposing.
Okay, and just in connection to what Paulos also asked, when you're looking at free space communication, you talked about turbulence and then, humidity, etc. will also affect. So in the experiment that you carried out in your laboratory, what was the length over which you did these measurements? And did you take care of humidity? For example, in the laboratory, you understand, we do have dehumidifier, etc. But did you get the level of humidity, etc. And how does it affect? Any such study you have or anything you would like to comment? Yeah.
See, right now, we try to modify the phase profile by creating artificial turbulence. Okay. Humidity more or less remain constant. And I think what is important when we consider a realistic communication system, what will be important is the the factors that can contribute to a high frequency change in the profile. If suppose the effect, let's say temperature or humidity, if it is leading to a change maybe once in several minutes, then that is not going to be a real problem. So probably that is why, of course, if you are thinking about a communication system that is running for hours and then by using no reference, then of course you have to take the slow effects also into account. But other than that, we have to see that what are the causes which can change the phase profile very rapidly. And the turbulence or this kind of the similar effect leads to a change at the rate of some few hundred times a second. So up to that part, a change in the phase profile at a rate of few hundred times a second can be taken care of by our system. So if, let's say, if there are some changes which is taking place maybe at kilohertz or more than kilohertz, then probably we will be reaching the limit of our scheme.
Yeah. Okay. Thank you. Paulos, you still have one more question? I see your hand.
I was just wondering the wavelength. Which wavelength are you using, and then is it stable all through the optical spectrum?
Right now, we used 532 nanometer because of the obvious reason that 532 nanometer is tuned for the best aberration correction with the optics that we are having. But I think when we'll be attempting the long distance communication, we will try to use the higher wavelength, maybe deep red, something around 650 or 660 nanometer, so that the effect of scattering is less.
Okay, so thank you, Basant. I think we have a little bit overshooted with the time, but thank you very much for the very nice presentation and answering the queries of some of the audience. So thanks a lot.
Thank you.
So now let me invite our next speaker, Dr. Shovan Chakravarti. Dr. Chakravarti obtained his PhD from the Saha Institute of Nuclear Physics, and his research interest includes astroparticle physics, high energy astrophysics, neutrino oscillations, ultra high energy neutrinos, and dark matter. And because you could see that there are lots of neutrinos involved in his expertise, so it's quite apparent, and everybody understands that neutrinos have a very important role to play in this in the study of supernovae and the in general about how does the universe works. So it is in this connection that Dr. Chakrabarty and his graduate student Madhurima Chakrabarty and their collaborators from the Munich Max Planck Institute Munich and Northwestern University, they published an interesting work which is related to understanding the role of these neutrinos in the death of stars. So the paper titled Fast Flavor Conversions in Supernovae, The Rise of Mu Tau Neutrinos was published in Physical Review Letters. And his today's talk is basically based on this work only. The title of the talk is Supernovae Neutrinos, a Flavorful Test. So now I request Dr. Shovan Chakrabarty to please share his work with us.
Yes. Thank you. So are you able to see my slides, and can you hear me properly?
Okay. Yes.
Yeah. Thank you. So firstly, let me thank the department for this opportunity and this nice introduction. So what we are going to talk about is based on this work, as already mentioned. So I have given this name a bit of spin for the title of this talk, which you can see like supernova neutrinos, a flavorful test. So I'm going to explain this each and every part of this title in the next 10 slides. But before that, like just to summarize, what we are going to talk about is this neutrinos from supernovae from these during stellar death, and these neutrinos, as we know, have different flavors. So before this work, I mean, most of the would be like a bit conservative, say like almost all the works were actually done only for 2 flavors. We actually extended it to the 3rd flavor and found that there are some interesting effects, and that's what we are going to discuss about. So let me first introduce neutrinos, because I see like there are students from all the different branches in the physics department. So neutrinos are, as you might know, are the one of the basic building blocks of the standard model of particle physics. You have like these 3 charged leptons, electron, muons, and taus, and their corresponding neutrinos and antineutrinos, that is nu e, nu mu, and nu tau, and nu e bar, nu mu bar, and nu tau bar. So basically you have these 3 species of neutrinos and their antineutrinos. And what else we know about these neutrinos? They are basically chargeless. So it is a very important property if you are looking them from the point of view of astronomy 1, because like then these neutrinos can actually escape the extremely ionized environment of the star, where can be a lot of magnetic field effects, and moreover these neutrinos are also weakly interacting. So since they are extremely weak in interaction, they will have minimal scattering. So you can actually find neutrinos, or can actually study neutrinos from the very interior of the star, from where any other form of information may not reach to you. So these are like extremely excellent astronomical messengers. So this whole idea of this neutrino astronomy which has come up. And another very important thing in this regard is that neutrinos are almost massless. So they are in the beginning, they are considered to be like almost massless, and this implies something called neutrino oscillations that we are going to come in the next couple of slides. But then before that, let me tell you what are the different sources of these neutrinos. So neutrino, as we know, like they can come from sun, they can come from the very early universe. When in the atmosphere you have cosmic rays colliding with our atmosphere, you also create neutrinos called the atmospheric neutrinos. In fact, from the core of the earth, you can also have neutrinos which are known as the geoneutrinos. Then there is man-made neutrino sources like the reactors, accelerators, etc. But of course, like from this whole range of neutrino astronomy, in sense like supernovae, from gamma ray burst, ultra high energy neutrinos can actually come. So what we are going to focus on our work is about these neutrinos from the supernovae. But before that, let me just remind you all what is this neutrino oscillation thing. So neutrino oscillation was actually first was seen, for example, for the neutrinos from Sun. So you can actually calculate how many neutrinos you are going to expect from Sun. And when the discovery was made, as you can see in this top left slide, the expected number of the neutrinos in the argon detector was actually much larger than what was the observation below in this blue band. So this was actually from long time known as the solar neutrino puzzle, and this was actually in fact, this discovery was actually part of this Nobel Prize, which was given in 2002 for neutrino astronomy. Discovery, in a sense, like discovering the solar neutrinos, and these solar neutrinos were actually indicating something more interesting than simple that the sun can actually create neutrinos. Is that like there is some more physics involved in this in the solar neutrinos. So the solution to this discrepancy or the solar neutrino puzzle came out from in this way, that people realized that neutrinos can actually flavor oscillation, and basically these electron neutrinos from sun, they can actually mix with other flavors, and this mixing can be of resonance kind in the sun because of something called MSW effect. We don't need to go to those details, but the basic idea that neutrinos which start at one flavor, but they can appear in a different flavor as they propagate. Similar discoveries were also made for the atmospheric neutrinos. In fact, the Nobel Prize for 2015 was given for discovering these neutrino oscillations, that which actually indicated that neutrinos are massive. Now, we realize that neutrinos can actually move from one flavor to another flavor, but then how are they connected to this supernovae? Right. So supernovae are like, in fact, like one of the most interesting astrophysical objects that human beings or like early astronomers are seeing for a long time. So one of the most famous is the supernova 1054, which came at like 1054 AD, which is present as we'll see as the Crab Nebula. The Chinese astronomer and many other astronomers from different civilization at that time has seen this strange star coming up from all of a sudden, and then slowly the intensity of that new star is actually diminishing. So this we have realized from that early observations, and there are many other accounts of like almost every century there is one supernovae in our galaxy, and that people have seen. So we are actually observing this supernovae, and of course, like with the modern astronomy, we are able to see supernovae from distant galaxies far away in the universe. But how are they connected to these neutrinos? Now, for that, let us have a very quick look at this, how the supernovae are actually formed and what actually happens. What is basically supernovae? The supernova is nothing but like the terminal phase of a massive star. When I say massive, it's like 8 to 10 times massive than the sun. And these are like one of the most energetic events in nature. You are expecting something energies of the order of 10 to the power 51 arc being emitted from such events. And the basic model for this kind of event is that, like, because of this nuclear burning, you have all these different materials, and the heavier one goes to the center. So you can see like iron at the center and hydrogen at the outer envelope, and you create this what you call this onion ring like structure. And I have chosen these pictures. I mean, there are other pictures also from the Wikipedia page. So those of you who are interested can actually go back and can see those pictures there as well. So now what happens is that like this kind of onion ring-like structure, it will collapse due to its own gravity. And finally, in a shockwave driven explosion, it will actually eject the outer mantle, and this whole star will burst. So what is the basic picture of this thing happening is that you have this onion ring like structure here. At the center you have this iron core, and this iron core, because of its own gravity, starts collapsing. And once it starts collapsing, what happens that like you are slowly, your density is increasing, and at some point you reach a nuclear density. Now you cannot compress a matter beyond that point, so what will happen at this time, there will be a core bounce and a shock wave will be actually coming out, and the shock wave, in case of like smaller stars which have been seen, they can very successfully throw away the material which is outside. But then the problem of this picture is that, like, it has been seen, like as you can see this fifth picture here, that the shock wave actually stalls in most of the calculations after some time. But then, of course, we are seeing supernovae in the universe. So that means there must be a way that this shock is actually revived and it can actually reach the outer mantle. What I'm trying to say, like, basically, this shock stops inside that core itself. It cannot go beyond, say, like a very small radius, like few hundred kilometers in most of the supernova simulations, when you are actually talking about stars which are massive than, say, like 10 solar mass. But in nature, we are seeing the supernovae happening. So nature must have some way of reviving this stalled shock. And here comes this neutrinos. So neutrinos are basically created in many processes inside the star. And what is expected that these neutrinos will actually carry almost 99% energy of the gravitational collapse of this star. And that calculation actually shows that these neutrinos should have energy of the order of, say, like 10 MeV. They are these neutrinos, and their emission time, this whole neutrino emission happens of the order of like in 10 seconds. So this was the basic idea or like basic picture of how a supernova takes place. And of course, like in 1987 in February, which is like just a couple of days back in 23rd February. So this the star in one of our neighboring satellite galaxies, like what happened, that it actually became a supernova. And this is known as very famously known as the supernova 1987A. But then people thought, okay, but there is this prediction of neutrinos should also be seen when there is a supernova near to us. Of course, if you are talking about very far away supernovae, the neutrinos cannot reach us because their fluxes will decrease at 1/d square, right? Whereas as the distance grows, the fluxes will be smaller and the detector may not be able to detect if the supernova is not reasonably nearby. And this was like of the order of, say, like, if I remember correctly, some 50 kilo/sec order. And you are expecting some neutrinos coming from them. Then people looked into this neutrino detectors all over the earth at that time in 87, and they indeed found that exactly correlating to that supernova burst, there was neutrinos which were actually detected in those detectors at that time. And this is known as these very famous neutrino events from the 1987A. And indeed, those neutrinos were of energies of the order of 10 MeV, and the emission time was 10 seconds. And Masatoshi Koshiyama got this Nobel Prize in 2002 for together with Raymond Davis Jr. for the solar neutrino observations, was what I mentioned before, for this observation. So now we see that neutrinos are actually being emitted from there. But how are neutrinos connected to this puzzle that our shocks are actually stalling inside the star? So here is like one picture of that. So you have this shock wave, which is so this green one this blue one is basically your iron core at the center, and a part of that had actually collapsed, and you have actually matter has been actually dissociated. And say now when the shock is actually trying to move out, it has to move through this iron, which is actually outside that collapsed core. Now when the shock has to move through this iron core, it will dissociate the iron, and you will create all these other dissociate particles like alpha particles. This will be a soup of plasma. But then the shock is going to lose a lot of energy while doing that. In fact, this is lost. So, I mean, one can actually show, as I said, like you are going to lose even for 0.1 solar mass of iron, you are going to lose almost the energy which is of the comparable gravitational collapse energy. So there must be some other way of giving energy to the shock, because we are seeing supernovae all around us. So the idea is that these neutrinos which are now coming from this core are actually doing this extra thing, because they are the ones who are carrying almost the whole energy of this gravitational collapse. And while coming out, they actually interact with this. Yes. Okay, so while coming out, they actually interact with this with this material, and they actually dump a part of their energy here. So in this lower panel, left hand side, you can see this picture. These blue neutrinos which are coming out here as is shown from this collapsed star, and outside in this green arrows are showing that is accreting matter in this collapse in this collapsed core. And now these neutrinos, while going out, they interact with this ambient matter and they give energy, and this actually helps the shock to come out. Now this picture is being tried in different simulations, and this is called the neutrino heating mechanism. It was proposed much earlier, as you can see, in 1966, but then how to actually incorporate it into the hydrodynamic simulations. So this is what people have started doing from certain almost like 3 decades now, and now they have moved into this understanding this convective process and a hydrodynamic instability. So this convective process, which starts because if you have a 2-dimensional supernova simulation, and this hydrodynamic instabilities together with this neutrino heating can actually help this supernova to burst. But as I said, I mean, even after 3 decades, what people are looking at are only 2-dimensional supernova simulations. So basically, just right now, say like in 2020s, the simulation is now moving into a 3-dimensional one. So it will take like another decade, and hopefully another decade we will know more answer. But then the point comes, like, how can these neutrino oscillations that I described before can actually be helpful? The way it can be helpful, as you can see, here is the spectra of neutrinos which are coming from a supernova burst. And as you can see, the nu x, what you are calling as nu x, is basically nu mu, nu tau, and they are antineutrinos. They have a larger average energy in this blue one, say like of the order of close to like 20 MeV, considered compared to this electron species, which has like average energy of the order of say like 10 MeVs. So therefore, if you can now oscillate some of these X-flavored neutrinos into E flavor, you are going to have larger average energies or larger energies for the electron species. And as we know, this electron species will have like more efficient interaction with the ambient material. They can actually dump more energy. So it is kind of known that these neutrino oscillations behind this stalled shock can actually help the supernova to actually in this neutrino heating mechanism. So now this is the basic picture, and now we are going to see when the supernova neutrinos are emitted during the propagation, basically how this oscillation can actually affect it. Now, I mean, the picture is given, and now I'm moving into a bit of technical things, and I have to show like maybe few equations. So those of you have like really now tired from this long talks for last couple of hours can maybe take a rest if you are not want to go through these details. But what are the details? So the details are this, like, so this oscillation, as I already mentioned, actually is like what is known to us is vacuum and MSW oscillations, which happens for neutrinos, like our normal kind of oscillation, which is happening for like in when you actually do an experiment with a neutrino beam, or you actually have these neutrinos which are coming from some sun. And in that case, the frequency of these oscillations one can actually show connected to these parameters like delta m square by 2ic. But I mean, I don't want to go into the detail of this, what is the delta m square ATM, but this is connected to the neutrino masses. And what we are actually going to see that this kind of oscillation frequencies are like of the order of like 0.5 kilometer inverse. So they are actually in kilometer inverse order. But now, if you look into something very interesting which can happen only inside the like a supernova kind of scenario, or in an early universe where the neutrino densities are so large that the neutrinos can actually interact with other neutrinos. For example, this MSW effect, what happens in sun is like neutrinos interact with the ambient electrons. But here I'm talking about neutrinos interacting with other neutrinos. And if something like that happen, one can actually show that this oscillations does not depend on this delta m square ATM or the masses of the neutrinos, but depends actually on the neutrino densities. The frequency is governed by them, but more interestingly, you can see these frequencies are of the order of centimeter inverse. So you can actually have oscillations at much faster, and this is actually called something called the fast collective effect or collective oscillation. The reason it's called collective, as you can understand, these frequencies does not depend on the energy. So neutrinos of different energies will actually, all of them will show this kind of frequencies, or all of them can actually have these oscillations together. On the other hand, like when I'm talking about the vacuum or MSW kind of oscillation, they depends on the particular energy of that neutrino. So this was actually proposed by us in 2015, and this is like something very unique. But I mean, it does not mean that these neutrino oscillations are not affected by the masses. But all I'm saying that here, in principle, you can have oscillation in a collapsing stellar core, even if the neutrinos were actually massless. Okay, so this is what you known as the fast oscillations. And how are these oscillations taking place? So what I'm talking about, this oscillation is happening very close to the core. If you look at this schematic diagram, and very far away from that core, we will have this oscillation, which is very similar to the what happens in sun, called as the MSW oscillation. So these neutrino oscillations are happening in a separated region, this new interaction 1, or this fast collective oscillations happening very close to the core. Now, a very basic picture of what is happening. What you have here is, this is basically a neutrino gas, and you want to see and like how their evolution is affected. What you have is this Schrodinger-like or Liouville-like equation, where rho is the matrix of the densities of these neutrinos. And of course, you can understand that the diagonal elements is going to give you the total flavor content, because now we are looking into the flavor picture, the flavor space, if there is any oscillation, and the off diagonal elements are going to talk about if there is any oscillation. And this problem in principle is a very complex one, because here you actually have also the time variation. I mean, the picture, I mean, this is not in principle a stationary picture. And more interestingly, how does this Hamiltonian looks like? This Hamiltonian will have like 3 terms. The first 2 are like the usual. This is the what actually done for the vacuum one. The second one, NL, is basically depends on the lepton densities or the electron densities. So this first 2 are very similar to the Strander's picture. What makes this whole thing interesting and very different is this extra interaction term, where these neutrinos are actually having interaction with other neutrinos. So now it itself depends on the matrix of densities. So this whole picture now becomes a nonlinear coupled system. Of course, we are doing, I mean, this is something like a mean field one, and this is very similar to many other condensed matter system, and which colleagues in our department are definitely using. So, but then you can understand that this problem is bit more complex than a normal problem in a similar problem in materials, because now you also have to consider the geometry of the problem. So this integral is actually, these modes are not only dependent on the energies of these neutrinos, but they also depend on what was the emission angle, at which angle these neutrinos are emitted. So basically this V and V dash, this difference is going to take care of these angles. So my states, they are also angle dependent. So this actually creates a very difficult problem to solve this thing numerically. It's a very difficult numerical problem. But what happens, just to understand what can actually happen, here you can see a very simple example where you do not go into these complications. You just take like it's like a stationary spherically symmetric. We are basically looking into 1 + 1 dimensional problem. And then you can see here on the top panel you have the fluxes or the spectra of these neutrinos initially at when they are actually leaving. And this is actually an example from a slow collective oscillation, which happens not in centimeter order, but say like in a kilometer range. At what happens within like few hundred kilometers, you will find that these neutrinos between these different flavors have actually completely changed their fluxes. So as you can see, this black one was nu E, and nu X is this nu X, nu mu, nu taus, and they have completely changed their fluxes. But this is like a much more simple example. But then this fast oscillations, as I mentioned, actually happens because of this angular distribution. As I already I was talking about few slides back, these neutrinos are emitted at different angular different angles from the star, because it's not a point source, but rather they have a spherical geometry, and this angular distribution of these neutrinos become very important input. Here you can see, for example, in this picture, the nu e, which is a more if you're looking at certain distance from the star, the nu e will have a very different angular distribution compared to the nu mu and nu e bar. Now, what are the effects of taking this angular distribution? As you can see here, what I'm plotting in is here, you can see this is probability of these neutrinos moving to other flavors for some different parameters given by these different colors. And you can see within, say, like nanosecond time scale, these neutrinos can actually change to other flavors. So this is like an example of what can happen if you take these fast oscillations. So this actually came out to be very interesting, and after our proposal came, like in last couple of years, there are really almost like 60-70 papers which are written on these fast oscillations, and they can have many different implications. So one of the most interesting one is actually looking into how it can help the supernova dynamics or this failed shock. Here you can see in this orange or the yellow line is basically this new supernova density, the electron density, and this sharp discontinuity is nothing but the shock front. So the shock is now stalled somewhere between 100 and 200 kilometers, and these black lines are showing basically the parameter combination for which these fast oscillations can happen. So now you can clearly see just behind this shock front there is this black line which shows that it is possible to have this fast oscillation behind this shock front. And so we are plotting here the different parameters with the radius, and you can see this behind this stalled shock you can actually have this kind of oscillations, and if they would definitely change the neutrino heating in the problem. It would be more efficient. But then all these discussions were actually going into for only for 2 flavor neutrinos. However, but like what you need is actually a full 3 flavor test. But people are not doing that for certain reasons. That this as you can see, like, I mean, in this picture I was mentioning this nu x for all the different flavors. There was a reason for doing that, because what people found from hydrodynamic simulations that this nu mu, nu tau, and all these different flavors had very similar fluxes. So they were like justified of taking all of them to be same and considering this 3 flavor problem to an effective 2 flavor one. But there were like many times in past people have thought of doing a 3 flavor problem. There were some discussions on that. So here, like meanwhile Madhurima was working on this 3 flavor problem. And we actually found that how exactly these fast oscillations are going to change if you take, instead of 2 flavor, 3 flavors. For example, if you take one of the expressions, you can see this is like the flux of neutrinos and antineutrinos of electron flavor, flux of the muon and these new muons. Of course, if your flux of muon and the anti-muons are same, it's only depends on the electron flavor, and that's what people were doing. But we actually figured out how exactly these other flavors could actually change this dynamics. As you can see here, so this is a typical 2 flavor approximation where nu e and nu mu has a difference in their angular distribution, but sorry, nu e and nu e bar have difference, but nu mu and nu mu bar does not have any difference in their angular distribution. And if you take that, the picture would look something like that. But then why do we actually do that? So exactly around that time, people were actually looking into on these 3 flavor problems, and what they found in hydrodynamic simulations that it's not really difficult for the supernovae at these very high densities and these very high temperatures to create muons. And if you can create muons in there, you can actually create this. I mean, from the decay, you can actually find that there will be discrepancy between the muon neutrinos and antineutrinos. For example, if you look into the second top slide from on the right hand side, you can see these black lines which shows this difference of the muon and anti-muons in their simulation for if you do not take this extra muon creation. But once you take that into account, you find this very large difference, for example, in this for these red curves. So this difference between muon and anti-muons with and without a muon creation inside the star was found out to be significant. So we actually then we decided to implement these simulations for our nonlinear calculations. And then that's why I'm calling them a full flavor test. So these are like more like tests done because nobody has actually put both of them together and have seen what can actually happen. So in our test, we actually took different cases and saw what can happen. For example, here you can see what I have plotted in the y-axis is the off-diagonal element of this matrix of densities, and if you have this off-diagonal elements growing, that means you are having some kind of flavor instability, or you are having the flavor conversions can happen. So this blue line is a typical two flavor case, and you can see here this off-diagonal element grown from 10 to the power minus 10 to almost of the order of the diagonal elements. That is, you can have these flavor instabilities. But now if you take these three flavor conversions, these three flavor calculations based on these simulations by Bollig et al., we found that you can actually see there is no growth of these off-diagonal elements. So basically there will be no fast conversions for three flavor. In fact, however, there would be definitely cases where you can see like fast conversions in two flavor. This like the case 2, where fast conversions can also happen in all flavors. So what I'm trying to say, like this blue one again shows the two flavor case, this one, and here you can see this all three flavors. If you take a three flavor case, all of them can have oscillation, and definitely the effect would be different than this two flavor one. So we have done similar tests for other scenarios, and this test basically showed that these three flavor effects are quite different than this two flavor ones. So just let me summarize what we have mentioned. So these explosions in this kind of supernova scenarios are actually convectively supported by neutrino heating mechanism. So this is the present understanding how the supernova is actually burst. You have to have convection. That means you have to have more than one dimension, and there would be this neutrino heating. Together of them can actually be helpful. And this three flavor analysis of the fast conversion we found is not complete. The two flavor one is not complete, and one has to do a three flavor one to find the result. But the exact direction how this actually works would come from future muon simulations in 3 dimensions. The present ones are mostly 1 dimension, or some of them are doing 1 to 2 dimensional calculations. But like it would be like some time to really figure out how this three flavor effects exactly influence the supernova dynamics in detail. But qualitatively, the idea is that like your three flavor effects are important to understand them. So here is like one important thing I did not cover here is what about the detection, like supernova neutrinos production, oscillation and detection. And those of you who are like felt interested or wants to look into these students, you can actually look for this review, which is by Yas, which is pretty detailed, and it actually talks about all of them. And the detection part is really important, and which we could not, which I did not touch today. How do you detect this effect in different detectors at Earth? So like there are many different detectors, and for example in IIT Guwahati, like we already are connected to both the experiments, the future experiment Dune and then Hyperchemioka. Both of them would be actually able to detect many of the signatures of the supernova neutrinos. So with this, let me thank you all. Thank you all for the attention, and that's all from my side.
Yeah, thanks, Shravan, for a wonderful presentation. So now we are open for some very quick questions from the audience.
Yeah, Paulo's here. Can I ask?
Yes. Yes.
Yeah. Okay. Sovan, thank you for a very wonderful talk, and then it's very interesting. Just a couple of things which I have to understand. One, the masses. Are you treating them completely massless, or are you taking the masses
for the neutrinos?
Neutrinos, yeah.
Yes, of course. Like so what we are doing, like, okay. So here, so you are talking about, I think what you are asking, like in this fast oscillation. So are we actually taking the neutrino masses into account, or yeah? So of course we know neutrinos are massive from the oscillations, right? So in our calculations, of course, we took masses, and very interestingly, the masses actually happens, works like a seed for these instabilities. So these flavor instabilities, yeah. So masses, so the understanding. So very very beginning, like when 2015 we proposed, all our calculations were without masses. But then we realized, like when in a real situation, if you put these masses, they actually trigger these flavor instabilities. They act as a seed for this.
I see. And
these calculations are with masses, yes.
Okay. The question is actually then, the masses are not really known clearly, and then we don't know which one is higher and which one is lower mass, right? Normal hierarchy or inverted hierarchy, etc. So, is it sensitive to this? Like,
Very
for
interesting.
example,
It's a very interesting question. Yes. So I mean, since for right. So what happens is that, like, since this masses role here is only for triggering, and the rest of it, actually the whole thing is driven by these large neutrino densities. So they finally do not get affected by whether I choose what kind of mass ordering we are choosing. So in this case, of course, like if you look at, I mean, something which I did not discuss, what is called the slow collective oscillations, and they happen like of the order of few hundred kilometers from the core. They are highly affected by the masses and the mass ordering.
So it's because the profile.
Yeah. So I mean, so
it is more.
So what I mean, okay, the main difference what comes is like, let me go back, maybe where was that? Yeah. So the difference of this for the slow and collective oscillations comes from this angular distribution what I told you. So yeah, here. So this G was what you call the spectra, and the spectra basically means what is the difference, the spectra of like in individual flavors. Now, if you take these flavors to be independent of the angles, you do not have these fast oscillations. So this was the main understanding, that like once you take this instability, which can come into the angular part, the angular modes, they actually trigger, and they are really extremely fast, and they do not depend in principle on the mass choices. So I mean what you have, so the basic understanding is that the slow oscillations which happen at few hundred kilometers happens because of instabilities in the energy spectra, and and these fast oscillations happen because of the instabilities in the angular spectra.
Okay, so at some point you mentioned the difference between mu nu and mu nu bar, right?
Yes.
And I was actually wondering, since I would expect, of course, nu e is different, but for the nu mu and nu mu bar, what kind of thing will develop the change? I mean, difference in the density profile or things like that, because they may
yes. So this yeah. So I mean, so you can see like even without like so one thing is like what you can do, you can create these muons. I mean, these muons are created from pair production, and this is possible if you really have this very high. I mean, like you have to go to very rare. So initial idea was like when people used to do this supernova simulations long back, they did not talk about muon creation because nobody thought like you can really create muons in the supernova from pair production. But now this is two-dimensional one where there is a lot of accretion goes on, and there is the temperature actually goes above like few hundred MeVs, where you can actually create these muons. Now from this decay of these muons, you can actually create this, firstly this asymmetry, but there are the other effects of like nuclear recoil effects. There are some other effects which already give you some degeneracy between the muon and anti-muons in this, what you can see in these black lines. So these black lines are from the pictures without this extra muon creation. So the main difference which actually came in say last couple of years is like now you can think now it's not a scene to say like you can actually create muons inside the star.
Okay, so thanks. Yeah,
thank you.
Okay, so thank you, Shovan. So I think now we can close this session, and now I request Angna to please take over.
Thank you, sir. For the next session, I request Dr. Kadolkar to please take over the platform.
Hello, everyone. Welcome to this Young Achievers session now. In the final session, we have two talks, and the first talk is by Dr. Jaideep Ghosh. He recently completed his PhD from our department, and he was working with Professor Giri. He is going to join I am slightly having trouble pronouncing the name of this university, Sungkyon University in South Korea, for his postdoctoral position. He was awarded with Best Oral Presentation in WeCan organized by VIT in 2020. And his talk today is titled Color Tunable Perovskite Nanocrystals for High Performance Photo Detection. So I'll request Joydeep to now start his talk.
So Paulos has a raised hand. I think it's by mistake or something.
You forgot to lower you.
Yeah.
Am I audible?
Yeah,
Yeah,
Joydeep.
I can see you and hear you.
So thank you, our HOD sir and other organizer for giving me opportunity to present in this platform. So title of my presentation is solid state synthesis of color tunable perovskite nanocrystal and mechanism of high performance photo detection in monolayer MOS2 cesium lead bromide vertical heterojunction. So a metal halide perovskite are the direct band gap semiconductor having the chemical formula of AbY3, where A is a large cation, B is metal cation, and Y is halide anion. So this semiconductor have different advantage. So one of the most important advantage is it's a low cost solution process fabrication, and we can tune the band gap of this semiconductor over the entire UV visible region by changing the halide content, and this material shows excellent performance in solar cell. So perovskite solar cell have achieved power conversion efficiency over 23% now. This material shows very ultra fast photo detection with very high photo responsivity and fast photo response, and this material also shows very excellent performance in light emitting diodes. So these are a few applications of this halide perovskite. So solar cell, cell power photo detector, LEDs, and sensor. So here we have fabricated this all inorganic cesium lead halide perovskite nanocrystal by grinding method.